So what we're going to look at now is we're going to look at physics and antiderivatives. And so basically, we've been utilizing physics in order to give us a really great conceptual basis for understanding calculus, and also to give us some kind of like conceptual problems or real-world problems or examples that we can use in order to think really deeply about calculus because of how tightly they're related. Well, the same is true for physics and antiderivatives. The derivative of the position function is the velocity function. And the derivative of the velocity function is the acceleration function. Okay, we know this. This is something that we've been learning. So the antiderivative of the acceleration function is going to be the velocity function. It's like going backwards, right? Just like how when we go from little f of x to big f of x, it's going backwards. The same thing works in physics, right? Okay, acceleration, its antiderivative is velocity. And the antiderivative of velocity is going to be the position function. So if we take the antiderivative of the acceleration function twice, then what we get is the position function. Now what we should remember, right, is at each step of the way, each step where we take a derivative, we're going to lose information. So what we're going to need is we need initial conditions, okay? So if we're given the velocity and we want to find the position, we will need at least the initial position and sometimes the initial velocity if what we're given is the acceleration function. So if we're given the acceleration function, we're going to have to take the antiderivative twice. And so that means that we're going to be needing two initial conditions, right? The first, the initial condition for velocity, and the second will be the initial condition for position. But if we're given the velocity function and want to find position, then all we're going to need is just that initial position along with our derivative, okay? And basically, these two things together give us something called the differential equation, all right? Which are really incredibly powerful things. So let's look at a problem. A particle moves in a straight line and has an acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters per second, and its initial displacement is s of 0 equals 9 centimeters. Find its position function s of t. So we're going to start out at a of t equal to 6t plus 4. Okay? And we're going to take the idea, we know that v prime of t, the derivative of velocity, is a of t. So we want to find the antiderivative of 6t plus 4. Okay? So the antiderivative of 6t plus 4 is going to be, okay, 6t, we're going to add 1 to t, so this is going to become 6t squared, and then what that means is that we're going to have to divide by 2. 6t squared plus 2 plus, and then 4 is a constant, so that means its antiderivative is 4t. All right? And then we're going to have this plus c. Okay? So we're using that power idea for antiderivatives, right? We're going to, instead of subtracting 1 like we do with derivatives, we're going to add 1 to the power, and then instead of multiplying by the power, we're going to divide. Okay? Divide by this new power 2. So this is going to be my velocity function. This is v of t. All right? Now, this initial position, the initial velocity, v of 0, is going to equal negative 6 centimeters squared. So what I'm going to do is I'm going to plug that in to figure out what c is. That's one of the big things that we're going to do with these antiderivatives. So v of negative 6, or excuse me, v of 0, is going to equal 6 times 0 squared over 2 plus 4 times 0 plus c, and that'll equal negative 6. And so if I just do a little math, that gives me that c equals negative 6. So that's my initial velocity. Okay. What you'll notice is that when we have initial velocities, right, the velocity at time 0, in general, c is going to end up equaling that initial velocity. All right. So that means v of t is going to equal 3t squared, right? Because 6 divided by 2 is 3, plus 4t minus 6. All right. So that's v of t. Now we want to get to s of t, right? And we know that s prime of t equals v of t. So what that means for me is that means that now I'm going to actually go in and I'm going to take the antiderivative of v of t to find s of t. So 3t squared, that's a power one. So that means that I'm going to increase. I'm going to take 3t, and then this is going to go from 2 to 3, 3t cubed, and then we're going to divide by 3. Okay, plus, then t is going to go up by 1, so it's 4t squared divided by 2 minus 6t, okay, plus some constant c. So this is now s of t, okay? We're told that s of 0 equals 9. S of 0 equals 9. 9. And so this is going to be s of 0 equals, right, 0 cubed, because we'll just simplify. This will end up being 3t cubed over 3, so that's just t cubed. 0 cubed plus 2 times 0 squared minus 6 times 0 plus c equals 9. And so that gives me that c equals 9. So s of t, my position function, right, is going to equal now t cubed plus 2t squared minus 6t plus 9. And that's what we do. It's basically a matter of taking multiple antiderivatives. So there's my s of t, my position function. All right? A couple things to notice. Initial displacement means what's your position at time 0. Okay, so displacement is another way of stating position at time t. Is displacement. Okay? And so what did we do? Right? We started out with our acceleration function. We wanted to get to the velocity function, so we took the antiderivative of acceleration, all right? And then we plugged in the initial condition in order to find our constant, okay? Then, once we found our velocity function, we took the antiderivative of velocity to get our position function, okay? And then we set that equal to 0 in order to figure out what our initial condition was as well. And then that gives me my final position function, all right? And that's how working with physics works, basically, okay? Your position functions might be a little bit more complicated. We might have to do some more things with them. But basically, that's the idea. If we're given acceleration, to get to position, we're going to take the antiderivative twice, okay? And we're going to need 2 initial conditions, right? 2 antiderivatives, 2 initial conditions, all right? If we're given velocity, then we're only going to have to take the antiderivative once, and we're going to only need 1 initial condition. And this ends the lesson.